All right. Vertical asymptotes, here we go. So first, we'll take a look at one of the simplest functions that has an asymptote, f of x equals 1 over x. So just whip out your graphing thingy and graph y equals 1 over x, f of x equals 1 over x. Just to refresh your memory on it, let's see, here's my GeoGebra. Not GeoGebra, Desmos. I'll get those apps straight one day. F of x equals 1 over x. I get that beautiful shape right there. Does anybody know what that shape is called? It's got a special name, kind of like, it's a relative of a parabola. A hyperbola, yeah, that shape is called a hyperbola. That's correct. And this graph has both a vertical and a horizontal asymptote. We'll talk about horizontal asymptotes later in the course, but for now, we'll talk about vertical asymptotes. So a vertical asymptote happens when you take a limit as x approaches some number, and usually we're looking at one side or the other, so I'm just going to say I'm going at it from the right side, just for the heck of it, of some function, and you find that the result is either infinity or maybe it's negative infinity. So either the values skyrocket up or down. Okay. In a situation like this, infinity has a special meaning. So the y values in this case are what I'm describing. And so as x approaches a from the right side is what my limit is showing right there, then y is increasing without bound. Meaning there is no limit to how it can increase, right? And then we use the shorthand symbol infinity, goes up forever, or negative infinity goes down forever. So it could also decrease without bound. That would be a negative infinity. So in this case, infinity means to increase without bound. So if we look at this particular function here, and in particular, the limit as x approaches 0 on the right side of 1 over x, and we made a table for x and y, if we plug in 1, the reciprocal of 1 is 1. If we plug in 10, the reciprocal of 10 is 1/10. We plug in 100, the reciprocal of 100 is 100th, and so on down the line, right? If I plug in 1,000,000, what's the answer? 1 over 1,000,000, or 0.10s, hundreds, thousands, 10,000, hundreds, thousands, millions. Oh shit, I went the wrong way. Sorry. Scratch that. Try it again. Put those in backwards. I need to get to 0 from the right side. So I have the inverse of what I needed. X, Y. I want to do something like 1, and then 1/10th, and then 100th, and then 1,000, and so on, maybe millionth. All right, so what happens if you flip a tenth? What do you get? 10. So this just says 1 over x, take the reciprocal, so the y values are 1, 10, 1,000, that's better. 100, 1,000, thousand, or million. So as x goes to 0 on the positive side, y is doing what? It's increasing forever, right, without boundary, right? So we say the limit, we write infinity. Is infinity a number? No. So does this limit exist? No, it does not exist, but it does not exist in a special way. It increases forever. Okay? So you could say, at the limit as x goes to 0 from the right side of 1 over x, you could say it does not exist, but you can put a better answer there. You would say infinity. And infinity just means, in this case, go up forever, graphically. So this would be a better answer. It's a special way of not existing. Okay? It increases without bound. That's how it doesn't exist. And there's a few different ways the limits can choose to not exist. Guess what's going to happen if we go on the other side of 0? The limit as x approaches 0 on the left side. Yeah, at negative infinity, meaning it decreases, it drops without bound. So I'm going to put negative infinity there. That means y decreases without bound. Or it just drops forever. Okay. All right, we put those two facts together, and we try to write a result for x approaches 0. So here I don't mention left or right. What can you put for an answer? Yeah, since the left side doesn't do the same as the right, we can't say it's infinity or negative infinity. Now we get the generic does not exist. Because it's doing two different things on each side. All right, let's try another one like that. Let's consider the limit as x approaches 0 from the left side of 1 over x squared. So draw a picture, look at your calculator, figure out what's going on there. Do it two different ways. So I plugged in a couple of numbers, -1, -1/10, -1/100th, and 1 over x squared said, okay, the y value would be 1, then 100, then 10,000. What does it look like happening here on the left side? It looks like it's increasing without bound, right? So increasing forever, that's what infinity means in this case. And if we check out the graph as a backup to that, and we throw a little square on that x there, we can see, yeah, that on the left side, this thing is going up, 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 up as x gets close. Right? And I can put the point there and I can watch it move up, 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 and it goes right off my screen as I try to move it there. Everyone with me on the graphical idea here? So I'm going to steal that snapshot into my screen and just draw on it for a sec. Black, blue. Yeah, so as x creeps toward 0, the y values are creeping up higher and higher and higher forever, and I have that vertical asymptote, that wall this function can't cross. Coincidentally, what's happening on the other side? Same thing. So now if I say, well, what about the two-sided limit as x goes to 0 from either side of 1 over x squared? Can we be more specific than does not exist? The answer is yeah, we can say infinity. So if this was a test question and I said, hey, what's this limit? And you wrote does not exist, I would say you're half right. It doesn't exist. Infinity is not a number. It's a direction. In this case, up forever. Infinity would be a better full credit answer. Not too bad? Okay. Stuff you've seen before, we're just writing limit notation for it. All right, next one, which vexed a few people in the homework. The limit as x goes to pi over 2 of the tangent of theta. So visualize tangent of theta. If you're drawing a blank, then whip out your calculator. EAN parentheses x. Oops, did I throw a theta in there and an x? Oh yeah, I'm mixing my variables there. So technically, anybody know what this would be equal to? If there's an x and a theta and they're different variables? Since there's no x's here, the limit doesn't affect anything, so the answer here technically would be the tangent of theta, because there's no x's in that expression. Okay, so that was an accidental trick question. What it should have said is the limit as x approaches pi over 2 of the tangent of x, yeah. The variable that's moving has to match the variable in the equation if you expect something interesting to happen. Okay, graph. All right, so I'm going to graph x equals pi over 2, which will be a vertical or horizontal line? Vertical. Good job. It's vertical. X equals pi for pi over 2. And there's that line right there. So what I can see looking at the graph is the tangent's doing one thing on the left side and another thing on the right side. So just looking at the graph, what can I say the answer has to be here? It does not exist. Yeah, so this two-sided limit does not exist. Now the one-sided limits explain why. So if we look at x goes to pi over 2 on the, let's say, left side of the tangent of x, I'm just going to explore that numerically on the screen, but we can see what's happening pretty clearly. So I want to pick numbers less than pi over 2. So, and I want to figure out what is f of that number. So like 1.57 would be less than pi over 2, and I get 1,255-ish. If I did f of, what should I do next? You say that says 1.570796. Give me another number to plug in. 70. Yeah, so something bigger than 1.57.
Or no, I meant to say, sorry, 1.57011.
1.57011. Yeah, so that is bigger than the number I plugged in, but smaller than that number right there, because that's I can't touch that number, and I don't want to go past it either. And I can see, yeah, I get a big number there. This would be a mistake. Watch this weirdness. Some days when I haven't had enough coffee, I might look at that right there and want to round that 0 to a 1. What happens when I round that to a 1? Did I exceed pi over 2? Yeah, I just jump to the other side, and so then weird shit happens, right? F of 1.571. Ooh, all of a sudden I'm on the other side, and I'm plummeting toward negative infinity, or at least one step toward it. Yeah, so I could go 0.79. That would be a little on the left, and I can see the y value is getting bigger. Okay, so I'm just checking it out numerically. So on the left side, what's a better answer than does not exist? Infinity. I'm sorry, left side. And then on the right side, all right, left and right challenge. You're going to correct me if I screw that up ever. Pi over 2 on the right side, the tangent of x is dropping forever, decreasing forever. Since they don't do the same thing, we can't say it's infinity or negative infinity. We just say it does not exist. Okay. All right, that was exciting. Moving on, we've got some other fun stuff for today. We're going to take a look at properties of limits and then some special algebra that we can throw at limits when they're confounding us. So I'm just going to list a bunch of properties and we'll play with them. We've experienced these properties in practice. I'm just kind of formalizing them. If we take the limit as x approaches a of something like 2, if you think that's y equals 2, right? It's a horizontal line. What's y always equal to? No matter what x is, so that would be 2. So the property we get out of that is that if we take a limit as x is moving, and it's a constant function, let's call it c, and then you get that same constant answer. Nothing changes. Constants just hang around. Limit as x approaches a of x. If x is going to a, so x gets replaced by a in the limit, it's just a. Just a. Because x is going to whatever that number is. That's another powerful one. So those are the two most primitive properties we've got. Constant horizontal line, y equals x, basic straight line. Some other important limited properties, and I'm stating them in a slightly different order than in the book. If we have the limit as x approaches a of b times, so b is just some number, times a function of x, it turns out that constant multiple doesn't change things much. We saw that with some limits last week. So this would be the same thing as b times the limit as x goes to a of that, whatever that function is. So example of this would be something like limit as x goes to 3 of 5x. But we know that x is going to a 3, right? So what's happening to 5x? Well, it's going to be 5 times 3, or 15. Right, so you can basically take that constant, pull it out, and ignore it in the limit and say, well, what's x doing? X is just going to 3. Oh, okay, so we must be going to 5 times 3 or 15. So that's a simple example of that right there. Other important limit properties is that if you have multiple functions going on, so if you have the limit as x approaches a of f of x plus g of x, I'm going to put parentheses around those suckers, meaning I'm finding the limit of the sum. Turns out that's the same thing as the limit as x goes to a of f of x plus the limit as x goes to a of g of x. Sort of. There's one catch here. The catch is that both of these limits have to exist. Right? If they don't exist, how can you add two things that don't exist? Can't do that. Weird shit happens. So this is provided. These limits exist. So that's super important. So sticking with this provision, because I'm going to use combinations of functions a couple more times here. What if I take the limit as x approaches some number of f of x divided by g of x? As long as those functions behave well, meaning they have the numerator is okay and the denominator is okay, then this is going to be the limit of the numerator divided by the limit of the denominator. As long as those two limits exist. There's one more catch here. What am I hoping g of x is not equal to?
0.
Yeah, better not be 0, otherwise we get trouble, because then I have opened up another can of worms. So as long as this limit in the bottom is not 0. Okay. Both limits have to exist, the denominator can't be 0. I know this is exciting. The limit as x goes to a of f of x times g of x. It's equal to the product of the limits if those limits exist. So same idea, limit of f of x times the limit of g of x. And then some other funky ones. Limit as x goes to a of the square root of f of x. So as long as f of x doesn't end up being a negative number, because square root of a negative number means we have to play with I, and that's a whole other problem, then this is equal to the square root of the limit. We can slide that limit inside the square root. And the catch there is this interior right here can't be negative, which means it has to be greater than or equal to 0. It can be 0, that's all right. It can be positive, that's okay. We just don't want it to be negative. Otherwise we have trouble. Now there's nothing special about the square root. Actually, cube roots are easier than square roots, because cube roots, they don't care if things are positive or negative. Okay? What's the cube root of -1? Almost. It's -1. Yes, cube root loves negatives. It's great. But the square root of -1, that's where I pops up, and that's a problem. So we can generalize this and say as x approaches a, if we take any root of a function, oops, get ahead of myself, combining two parts of the function. And that's going to be equal to the nth root. We can slide that limit inside. If it's an even root, we got to worry about negatives. If it's an odd root, negatives aren't a problem. Right? And that's something we're used to from our previous life in algebra. Another one that's kind of nice and related to that is if I take the limit as x goes to some number of some function raised to a power. Could be 2, could be 3, could be 4, could be 100. Turns out powers are nice things. I can slide that limit in and then raise it to the power after. So those are the basic limit properties. They're summarized in the book if you want to see them in one place. So we're just going to apply those properties to a few different problems until we run into other issues, and then we'll learn various tricks after that. So example, let's take the limit as x goes to -2 of 3x squared plus 5x minus 7. So we have limit properties that allow us to jump through addition. And subtraction is just adding the opposite, right? That means we can jump through subtraction. So one of our limit laws says, hey, this is the same thing as the limit as x approaches -2 of 3x squared plus the limit as x goes to -2 of 5x plus the limit as x goes to -2 of 7. Then we have other properties we can apply to each of these. Like what can I do with this 3 right here? And slide that out and just think about 3 times the limits x goes to -2 of x squared. That 5 can pop out. 5 times the limits x goes to -2
I guess that's a minus.
of x. Where are we at?
Yeah, you're missing a minus.
Is it minus?
Oh, that should be a -7 there.
Okay.
Yeah, thank you. And then here, that limit's pretty lame. It's just -7. Here, you could do it in a couple of different ways. You can just think about what's happening with x squared when x goes to -2, and I think we can all think pretty clearly that's probably going to be 4. Okay. Or we could slide in and take the square out. What's x going to? -2. So this property says put the -2 in here and then apply the square. -2 squared is 4. So in the end, we get 3 times 4 plus 5 times -2 plus -7. Which the limit property is basically this ends up being like just evaluating the function at -2. Okay. What is it? -9? So the moral of this story here is that polynomials and limits work well together. So if p of x is a polynomial, then the limit as x goes to any number a of p of x, is just whatever p of a is. Just plug it in, you're done. We played around with a couple problems like that in the last section. All right, so polynomial just means you have the sum of powers of x, and maybe some multiples in there. Next, what if I have something like the limit as x goes to 3 of x squared minus 1 over x squared plus 1? Do we just go over any properties that apply here? You could factor if you want, yeah, but forget about factoring for a minute. there's a property that covers this. It's a few pages back. Yeah, you just take the limit at the top, take the limit at the bottom, see what happens. Okay, so I can rewrite this as limit as x approaches 3 of x squared minus 1 over the limit as x approaches 3 of x squared plus 1. And this is legal, this equal sign right there, provided both of those limits work. I don't know they work yet, I'm just hoping they do. I may have written something down illegal. But what kind of function is the numerator? Is it? It's polynomial. What kind of function is the denominator? Polynomial. What do we know about polynomials? You just plug in and go. So I just plug in 3 to the numerator. I get 3 squared minus 1. Plug in 3 to the bottom. I get 3 squared plus 1. 9 minus 1 is 8. 9 plus 1 is 10. So this goes down to 10, 8/10, or if you like to reduce fractions, it would be 4/5. Oops. If you prefer decimals, it would be 0.8. Take your pick, they're all nice. Didn't need to worry about factoring because the numerator was a polynomial, the limit existed. The denominator was a polynomial, the limit existed. And even better, something I skipped, the denominator was not 0. Otherwise, I would be thinking, oh crap, it's 0 on the bottom. I hope I can factor my way out of this, which we did. We played around with that last week. All right, so limit laws are kind of boring at first glance, but they allow us to quickly and easily look at a bunch of different functions and just cheat and plug in. So some other interesting limits. Let's try the limit as x goes to 3, again, of x squared minus 3x over 2x squared, let's just be minus 5x minus 3. All right, see what you got on that one. Oh, by the way, on the previous step here, are you guys lazy sometimes? Meaning you don't want to do any more than you have to because you have very busy lives? Yeah, that's my interpretation of laziness, right? Because I'm just a busy guy. Usually I think this step as opposed to write it down explicitly because that was a lot of ink, right? On a test, I might slow down and write that down to kind of make sure I'm getting all the pieces right. But, all right, go for it. Think your way through it, write something down. Numerator 0, that's not bad. What's the denominator? Zero. Miss Chen, what should we do? If 0, I get 0 over 0 when I try to cheat. Because 0 exists, right? But 0 on the bottom's a problem. And sometimes 0 over 0 is 1, and sometimes it's pi, and sometimes it's 44, and who knows what it could be. So the limit property for the quotient rule doesn't work here because I get a 0 on the bottom. So pray factoring works. Factor your numerator, factor your denominator, see what you get. So if this is a test and you find out you get 0 over 0, don't just write indeterminate or leave 0 over 0, do something else. In this case, factoring was our next option. Pretty sure those are the factors of the numerator and denominator. Yep, that checks. So the nice thing about this version of 0 over 0, I can clean it up because they have a common factor top and bottom. The number divided by itself is 1. So this must be the same as the limit as x goes to 3, as long as I don't touch 3, of x over 2x plus 1. Now I have a polynomial in the numerator, polynomial in the denominator. I'm going to try the quotient rule again. Quotient rule says the numerator is going to 3. Quotient rule says the denominator is going to 7. Okay, so I think 3/7 might be the answer.
How do you do the factor?
How do I do the factoring?
Yeah.
I guessed. So I'll just slow down and do my guessing again. Copy that into another screen. So the numerator, I just noticed is a common factor of x. So I pulled the x out, that leaves behind x minus 3. In the denominator, to get a 2x squared, I was thinking it had to be 2x times x. And then the 3 had to be 1 times 3. So either it's 1 and 3 there, or it's 3 and 1. And I picked 1 and got 1. Right? So it's either 1, 3, or it's 3, 1. And then you have to decide if that's a negative, one of these is positive and the other one's negative. So it's either plus 1 minus 3, or it's minus 1 plus 3, or it's minus 3 plus 1, or plus 3 minus 1. So there's 4 different possible ways this could factor based on the things I see there. Yeah.
I've never seen a way to factor that.
You've never seen that method of factoring?
No.
That's called factor by guessing.
That's what I.
Yeah. So the other way to factor this, if you don't like factor by guessing, would be to say, what is 2 times negative 3? Negative 6. So then what you do is you look at all possible pairs of factors of negative 6 to get the middle. So that's either 1 times 6 or 2 times 3. Now the catch here is that that's a negative 3, right? So that's a negative 6.
Yeah.
If they're negative, that means they're opposite in sign. If they're opposite in sign, that means you have to subtract them. Which of these pairs subtract to get negative 5? Yeah, it's got to be 1 minus 6 is the magic pair. So if you're using that technique, then you're going to rewrite that sucker as 2x squared plus 1x minus 6x minus 3, and then you factor in roots. Is that look familiar?
I don't know that.
So then here, I'm going to get a factor of an x, which leaves a factor of 2x plus 1. What do these guys have in common, the second two? Negative 3, yeah, I got to take the negative out. Negative 3 goes into 6x, leaving a positive 2x. Negative 3 goes into negative 3, leaving a plus 1. Factor by grouping is successful if these guys match. Do they match? Yes. Therefore, that is one factor, and the other factor is whatever is left behind, which in this case would be x minus 3. All right, 2 forms of factoring. Good luck with that. If you forgot how to factor, I can show you some online resources. Moving on. All right. Next interesting one is the limit as x goes to oh, I think I told you this in the beginning of the quarter. One thing you get really good at in calculus isn't necessarily calculus, it's algebra. You get way better on all the algebra you've seen in your past life. And you get okay at calculus. Square root of x plus 1, no, plus 2, and then we'll subtract 1, and then we'll divide by x plus 1. Right. So we have shortcut rules that apply to all of this, provided each limit exists. Okay. So if we kind of cheat and plug in -1, what happens here? I get 0 over 0. Yeah. So if I cheat, I get 0 over 0. 0 over 0 is indeterminate. Sometimes it exists, sometimes it doesn't. Sometimes it's 5. Who knows? So a couple of tricks here. I think we tried a trick before where we factored with square roots. That trick doesn't work so well here. We're going to do another trick called multiply by the conjugate. Multiply by conjugate. And I think that's probably supposed to be a J there.
Oh, you did the J.
Okay, and so I need the conjugate of the thing that's the most trouble, which is the square root. Conjugate means change the addition to subtraction or subtraction to addition. Okay? So I'm going to ignore the limit for a minute. I'm going to take the original thingy, square root of x plus 2 minus 1, and I'm going to multiply it by its conjugate, the square root of x plus 2 plus 1. Now notice I put that little hook on the end of my square root. That's because when I get excited, I'm sloppy, and I need to clearly know where the square root ends, what's inside and what's outside. Denominator here is going to be x plus 1 times that same conjugate, because I got to multiply the same thing, numerator and denominator. Okay, focus on the numerator here. Multiply that out, see what you get. Ignore the denominator for a minute. You get 4 pieces in the numerator. So I get x plus 2. So the square root times the square root cancels. Get an x plus 2. Then I'm going to get 1 square root of x plus 2 from there, and then I'm going to minus square root of x plus 2 there. And then negative 1 times 1 is minus 1. Middle terms volunteer themselves out. They add up to 0. X plus 2 minus 1 is really x plus 1. So then skipping down a little bit, I get x plus 1 over x plus 1 times the square root of x plus 2 plus 1.
So you can cancel the x plus 1, right?
Yeah, so now I have a number divided by itself. I have a factor of x plus 1 in the numerator. What's a number divided by itself? 1. Therefore, this must be equal to 1 over square root of x plus 2 plus 1. Now, let's cheat again. What is x approaching back in the original problem? Negative 1. Can I sneak a negative 1 in now and hope it works out? The answer is yeah. If I plug in x equals negative 1, I get 1/2 for the whole thing. So as x approaches negative 1, this approaches 1/2. So in this case, 0 over 0 is 1/2. Like different every time.
So what happens if you get a negative number in the square root? Does that mean
If you get a negative number in the square root, then that means you have a problem because you have imaginary numbers. Okay, and I will not give you problems where you end up with imaginary numbers because that's a whole different version of calculus. Calculus with imaginary numbers is different. So we're not going to go there. So that means you went astray somewhere if that happens in this course. All right, not too bad. Fun algebraic trick. Multiplying by conjugates. Times it. All right, I'm going to jump right to some real fun stuff. Numerically, we took a look at x approaches 0 of the sine of x over x, and we discovered numerically it does what? Goes to 1. Right? And I said that's a fact. You just want to memorize that because it's going to pop up later on in the course. So what I'm going to do is I'm going to prove it geometrically. Okay? I'm going to use some geometry about the sine of x and show it's 1 without using the numerical analysis there. So to do that, I need to consider the origins of the sine, and there's 2 ways to look at the origins of the sine. One is by looking at right triangles, the other is by looking at the unit circle. My preference is the unit circle. And I'm just going to look at the first quadrant because the other 4 quadrants are pretty similar. So this is a quarter of a circle with radius 1, is what I drew there. And then I'm just going to pick some arbitrary angle there. Let's say that angle is theta. If that's theta, then if I drop a line straight down from that point over to here, that red line right there is the sine of x, or sine of theta, sorry. Switch variables. So the length of that red line is the sine of theta, because it is opposite, and I just made a right angle right there, right? Yeah. Anybody remember the idea of arc length from in trigonometry? So what I want to know next is, what's the length of that arc right there? What is it?
Is it sine, cos?
Nope, it's not sine.
Theta equals
No, I know, I was
radius.
Almost. It's the radius times theta. Yeah, the arc length is always just the radius times theta. What's my radius here? 1. So the arc length in this case is
theta.
theta. It's just 1 theta or theta. Yeah. So the arc length there is theta. So I'm going to make a note of that. Arc equals theta. And can you see, looking at this picture, that the arc length is always greater than that vertical line? Right? So looking at this right here, I can see that the sine of theta is always going to be less than theta. Okay, a little trick here. It's actually less than or equal to. If I divide both sides of this by theta, now I'm just going to stay in the positive quadrant here, so I'm just going to restrict theta to being a positive number there. Just going to look at the right side for simplicity. Otherwise, I have to do sign analysis, which is a little longer. If I divide both sides by theta, what do I get here? Sine of theta over theta has to be less than or equal to 1. Okay, that's kind of cool to know. It's not going to be greater than 1. It's got to be less than or equal to 1.
The same as the sine.
Yeah, and I just switched x for theta. So yeah, so that's I don't have its equal to yet. I just have its less than or equal to. Okay. So now I got to say, what I want to do now is, if I can go on the other side and say it's also going to be greater than or equal to 1, if something is greater than or equal to 1 and less than or equal to 1, what has to happen? It's got to be 1, right? So now I just got to check the other side. So here's how we're going to check the other side. So I'm going to redraw that picture. Do the other side. So unit circle again. Some arbitrary angle, theta, in the first quadrant. And again, you can put it in another quadrant. You just have to think about positives and negatives. And the book does this if you want to read more detail. Next thing I'm going to take a look at, so I know this is the sine right there, that altitude drop down right there, the sine of theta. If I were then to draw, I guess I'm going to draw a black line. If I go straight up from that point right there, does anybody know what the length of this line is? No, it's not the radius. It's another very famous trig function. Like the third most famous trig function ever. Tangent, yeah. Sine and cosine are like the top two, tangent's the next one. Yeah, and you can prove that if you want. I'm doing a little playing around with this new black triangle. It's the tangent of theta. Okay. And as I vary theta in that quadrant, what can you tell me about the relationship between the sine and the tangent? So I've got this, the sine is going to be smaller, right? Sine of theta over there, tangent of theta is over there. And if I consider that earlier I looked at the arc length sits in between those two lengths. Okay. So I get this inequality here. Okay, so now we're going to have a little fun with that inequality. We're going to apply some algebra to it. We're going to divide everything by the sine of theta. Can anyone see why I'm doing this here?
Yeah.
See, the middle thing is almost what I want. It's upside down of what I'm looking for here. Okay. So what's on the left here? That's a 1. I'm interested in the reciprocal of this guy, but we'll just leave him there for now, or her. Sine of theta. Can I reduce the tangent of theta over the sine of theta?
Sine over cosine.
It's sine over cosine, divide the sine out, what do you get? Almost.
1 over
1 over cosine. Yeah, it turns out this sector is 1 over cosine. Theta.
Ew, what is it?
All right.
yes.
Now, if we flip everything here vertically, that also flips everything 180 degrees too. So if I flip everything, I end up with the cosine of theta is less than sine of theta over theta, which is less than 1.
Yeah.
Which is
Now, I had already established that side over there. That's just a little bonus. But it's this side that is now powerful. Theta is going to what in this instant? 0, right? Okay, so then the question is, what is the cosine doing as theta goes to 0? Look up cosine. Cosine is the x value. Theta is heading down here. What happens to x when theta gets to 0? Yeah, this length right there is then 1. So now I have a 1 on the left side. So now what I have is, as I take the limit, I bound to the limit as x goes to theta of the sine of theta over theta is trapped like that. Now remember, the limit can't touch 1. It's just getting to the very edge of it. So that means the sine is, this limit has to go to 1, right? We squeezed it in. This is what's referred to as a squeeze theorem proof. We squeeze the limit to 1. Just because of the way the sine and the cosine and the tangent are related on the unit circle. Okay. Are you going to have to reproduce that whole proof? No. This is just the fun of taking calculus. You get to watch me do stuff like this sometimes. And guess what? We don't have time for fun with math. This homework assignment 2-3 is way shorter. I think you'll get through it pretty quick. There's a couple of algebraic trickery that's got to happen in the middle and near the end. Do your best, and if you have to get stuck on anything, we'll go over it tomorrow. William?
It's chapter 3. Yeah.
I just posted chapter 3, yeah. So if I go to the student view, you should now see that there is some chapter 3 stuff. And I just put a note down here that these last 2 sections I'm not quite done with, but the other ones I am. So you should feel free to poke around in there. All right, have fun, everybody. Do math.
But 2.3 is not, it's not, it doesn't.
So in chapter 2, we started section 2.3 today, laws of limits.
Yeah.
Yeah, so that's not chapter 3, it's just chapter 2, section 3. And we're gonna, so we'll answer homework questions on this tomorrow and jump into continuity also tomorrow. Okay? You're welcome. Good day. And Rob, if any algebra, Here, Rob, here. If you get stuck on algebra stuff and I didn't clearly explain it in class, just let me know.
Oh, I was stuck on the page marker.
Yeah.
Because usually when I factor,
Yeah.
it's